Next talk is given by my friend and colleague, Jan Stępień. And he's going to talk to us about mutation testing.
Thank you for this. Thank you for this warm welcome. Thank you all for coming here. Great to be here with you. Great to be again in Berlin. I'm here to talk about testing, but before I start, allow me to share a short story. Not long ago, I was booking my flights, and the airline asked me to provide my surname exactly as it appears in my passport. So I look into my passport, and I think, what can potentially go wrong? Well, this is the confirmation email I got back from them. So I'd like to point your attention to, first of all, like my surname has one special character reduced to 7-bit, and the second one just removed altogether. And the German word Bestätigung is botched in two distinct ways. Firstly, in the header, and then in the body below. So why am I talking about this? Well, because I claim that writing software, writing correct software, is really hard, and we are bad at it, right? We're writing really poor software. We try to address this problem somehow, either using tools like advanced typing discipline. But what we do often is we write tests. And in the Clojure community, we're quite good about it. When we create a new project, for free, we get one test namespace. Inside, there is a test which is broken, and we have to fix it. It's a good thing. Another tool which is becoming more and more popular in our community is property-based testing, which allows us to make general claims about our software and then subject those claims to a whole hail of automatically generated inputs. Here you can see that I'm testing idempotency of the sort function. Those are excellent tools, but they have one common problem. We still write tests, right? And as we know, we are bad at writing code, so how can we think that our tests will be any better than that? Who is in the end testing our tests? Who is increasing the likelihood that our tests aren't complete garbage? And this brings us to mutation testing, the subject I'd like to discuss with you today. Before I start, I would like to share with you two base hypotheses on top of which mutation testing is based. The first one is the competent programmer hypothesis. According to it, code written by us, by competent programmers, differs from correct code only by some few bugs, few faults we accidentally left inside. Thus, a good test suite will be a test suite which detects those few bugs, few problems in our code which make it imperfect. We could thus validate whether our test suite is good, is satisfactory, by manually inserting bugs and seeing whether the test suite is still green or it becomes red. We don't do it because we barely have time to write correct code. So having on top of that manually inserted bugs to verify whether everything is fine seems like quite a stretch. Well, what do we do in such situations? We automate things. Can we somehow automatically generate faults and insert them into our programs? And if those faults resemble faults we would have introduced manually, accidentally, then those automated faults will be good at verifying that our test suite has satisfactory quality. But then you might ask, there are so many ways you can introduce bugs into our programs. There are so many potential mistakes. And when you start thinking about combinations of those problems, suddenly you end up with a combinatorial explosions of faults you can introduce into your programs, especially sizable ones. This brings us to the second hypothesis, namely the coupling effect hypothesis. According to it, a test suite which would detect a simple bug in our program will also detect more complex bugs which are combinations of those simpler faults. Thus, complex faults are coupled to the simple faults by a test suite which would detect both of them. Thus, we don't need to come up with some complex bugs and introduce them into our programs to test the quality of our test suite. It's enough to introduce a simple bugs. And those two hypotheses bring us to mutation testing. Let's get vocabulary well defined. Mutants are invalid versions of our programs we artificially generate. We try to kill those mutants by running our test suite. If our test suite turns red, we know that it was satisfactory, it was good enough to detect a given mutant. Otherwise, the mutant becomes a survivor. And this survivor is something we have to look at. Is this something which isn't covered by our test suite? Or might it become a regression in the future? Or is it dead code we can just get rid of because we don't care about it? Either way, we get some actionable information. Mutation testing, like many things in computer science, like many good things in computer science, is several decades old. It was introduced in 1970s. Since then, over 400 scientific papers were written on the topic. Existing research confirms both the competent programmer and coupling effect hypothesis, thus giving backing justification to the entire method. I recommend taking a look at this review paper from which I learned a lot about the technique in question. Most of the research was invested into languages which were mainstream at the time of writing. So as you surely understand, most of the research went into C, Java, and Fortran. But still, there is a lot of existing tools for languages we are more likely to use today. Well, Java is, of course, something which is high on the list. There is PI test for Java. There are libraries for Ruby, a very mature mutation testing tool. And there are also tools for JavaScript. But what brought me to the topic in the first place was the fact that I haven't found a Clojure equivalent, a tool for random mutation analysis in Clojure. And with this in mind, I'd like to introduce Mutant, mutation testing library for Clojure. And this will be the topic of next couple of minutes when I'm going to discuss principles of its operation and share with you some problems which I ran into. Mutant works in 4 steps, more or less. It starts by reading all files you have in your directory, somewhere in your src directory. It loads all those files and generates mutants of all top-level expressions in those files. Afterwards, it runs your entire test suite, everything it finds in your test directory, against every single mutant, and then reports all survivors. That is, versions of your code I have artificially generated, and your test suite didn't detect problems which are inside. Let's take a look at details of all those steps. Let's start with generating mutants. In order to generate mutants, I use this excellent library called rewrite-clj. You might know it, but it's used, among other things, in Line Ancient, a plugin, lining and plugin for automatically upgrading your dependencies. An excellent tool for manipulating Clojure forms, be it data or code. But as we know from Franka's talk earlier today, it's the same thing. What I do is I start introducing bugs using not Line Ancient, but rewrite-clj. Given an AND, I might turn it into an OR. Given less than check, I might introduce some problem in the at the boundary. Given an empty predicate, I might turn it into a seek, which in a Boolean context is a negation. Finally, given any function more or less involved, I might just remove the body altogether. Then I compile this code. Then I need to reevaluate both changes I introduced and every single namespace which might have been affected by by those changes. Here, tools namespace comes very handy. It's a tool which allows me to build a dependency graph of everything I can find in both your SRC and test directories, and then recompile all relevant, potentially affected namespaces. At this point, I'm ready to run your tests. And here, I, again, find all the namespaces which I can find in your test suite, evaluate the tests, assemble the results, and finally demonstrate them in a following way. Here we see results of running Mutant on itself. I'm showing just 2 samples. You can see that, for example, in the rm-args private function, if I remove and replace it with or, my test suite is green. And if I remove entire body of the dependence function, the test suite is still green. I'm bad at tests. So I'm super excited, right? The thing works. I ran it on a number of prominent open source libraries we all know and use. And I got some really interesting survivors, actual, real cases of code which might become a problem should future changes introduce some regressions. I'm not going to name any names because that's not the point. My point is that the tool is already like, it's like a valid prototype, which is something you can use to mutation test, to run a mutation analysis on your projects. But before we get all too excited, let's talk about problems, and there is a lot of them. First of all, mutation testing is slow. It can be unbearably slow. Authors of a paper from 2001 suggested 3 main approaches to tackling this problem: fewer, faster, and smarter. Let's talk about details of all those 3 techniques. By fewer, they meant fewer mutants, that is, generating fewer versions of your code to run mutation analysis on, to run your test suite against. You can select what to mutate. You might want to you might not want to generate mutants from every single line of code, every single expression, every time you run the mutation. We will return to this topic soon, but I'm just hinting it as a valid technique. You might be more picky when it comes to your mutation operations. That is, maybe some things, like removing entire bodies of functions, isn't as effective because probably, unlike me, you have test cases which cover such problems. Other mutation operations might, on the other hand, be very effective, very efficient at finding problems in your test suites. You might sample your mutants. This is counterintuitive, but according to some research, if you just randomly take 10% of all mutants you generated, you get 80% of survivors back from the mutation analysis. In other words, you do 10% of the work, you get 80% of the results. So it might be worth looking in this direction too. Doing faster is something which we're doing which is happening already in case of Mutant. Not restarting the virtual machine is one intuitive thing. Thanks to how Clojure's namespaces work, we can reevaluate code in namespaces without restarting the virtual machine. Thus, the rest of your code just remains there in place. We're not paying time to restart the machine and warm up all of our code in a just-in-time compiler all over again. Another thing is running tests in parallel. Notice that after we've generated all the mutants of the code, potential candidates to run test suite against, we can just scatter them, distribute them across a cluster of JVMs which are responsible just for running code with a modified version, just running your tests with a modified version of your code, and then reporting back results. The method is the problem is pleasantly parallelizable. Doing things smarter is, well, the trickiest bit. What we can do is we can try to execute only relevant tests. That is, follow the dependency graph which we've built before, and try to, every time we run our tests, run only those which actually have a chance to kill your mutant, to kill a potential survivor. Some tests, some of your tests are completely unrelated to the code I mutated. If we can find those dependencies, we will save time because we will run fewer tests. We might reorder the test suite, and this is something which I find very interesting. We might try to record statistics as we're running the tool, recording which of our tests are most efficient at killing mutants, which tests are most likely kill mutants. And then reorder the test suite and have them run at the very beginning of our test suite execution. The moment we run into first red test, we know we can stop the test run because we already killed the mutant, so there is no point in continuing running all the remaining potential green tests. Thus, reordering can bring some return on investment. All those things are minor inconveniences compared to the fact that the entire method might not terminate. You can imagine that we might generate a mutant which has an endless loop inside. What we can do then? Well, the code will keep spinning, and we will at some point decide, well, maybe this is enough. Maybe we waited enough. Let's assume we accidentally created an endless loop. We want to just kill it. The problem is that the underlying virtual machine doesn't help us at all. JVM cannot reliably stop threads. There is a thread stop method in the Java API, but sadly it's deprecated and its usage is not recommended because of difficulties when it comes to portability of its implementation. There is a lengthy article in Oracle's documentation recommended. We might want to fork a new process and execute our test suite there. And should the process go into a loop, we might want to just kill it and move on. Well, it's not possible because JVM, for portability reasons, cannot fork. And finally, starting new JVM is too slow. We cannot just afford starting a new JVM for every single test suite we want to run. This would make already relatively slow method unbearably slow. Luckily, it's not something which happens frequently. So it's not something which will haunt you every single time you work with the tool. But still, it's something which I have in the back of my head because there is no easy and simple solution. It's still something I'm working on. But if despite those inconveniences you still want to invest into this method and try it out, I think that the best solution to try to incorporate the mutation testing into your development flow will be not as part of your regular, say, test-driven development cycle, not as something you do on your own development machine. Rather, I would move it to your continuous integration, continuous delivery pipeline, because I think this is where it really belongs. If we can introduce a dedicated part of our continuous delivery pipeline, which is responsible just for taking every single commit, every single branch we pushed, and then running mutation analysis on it, we can get extra information a bit later, but we don't have to wait for it, and it doesn't break our workflow at all. You submit your pull request if you're operating in a branch-based development cycle. You submit a pull request from your feature branch to master. You get a message from your CI saying, yes, everything is green, all your tests are cool. And then a couple of minutes later, you get an extra message saying, but there are still some problems in your I found here. Namely, if we introduce the following bug, a potential regression in future, your test suite will not catch it. Extra information increasing the quality of our test suite. There is one more thing. In our continuous delivery pipeline, we have access to what's very valuable. We know exactly what has changed. We know exactly which lines we touched every single time we pushed a new branch, we pushed a new commit. And I think this is very important, because this allows us to narrow down our mutation analysis just to files, just to lines, just to functions which matter. You don't need to run Mutant on the entire project. If you have a really large project, this will take forever. Instead, focusing just on concrete lines, just on concrete parts of your project allows you not only to make your mutation analysis much faster, but on top of that, you are running it on the code which matters, on the code which is relevant for you today because it's a code you committed, which you modified today. And this allows you to introduce the whole practice gradually. You don't need to cause an organizational-wide earthquake saying, from now on, we're doing mutation testing, and accept it because this is the way we're going to work from now on. No, you just add this extra thing happening behind the scenes, looking at your Git history, and just working on just running mutation analysis on a per commit basis, working on your newest code, working on code which matters now. And thanks to tools thanks to existing tools, for example, rewrite CLJ giving me access to line numbers and positions of code I'm creating, of code I'm modifying, I'm able to, Mutant is able to filter which lines of code you want to modify, which you want to subject to your mutation analysis. So the tooling is there. It's all about connecting pieces. It's still something on my to-do list, something which I want to ship in near future. This might sound to a degree like waving my hands in the air, but there are real-world scenarios of this technique being successfully introduced and helping a lot of people increase the quality of their software. One example is a code base at innoQ, where they had 100,000 lines of a C++ 3D rendering engine. They were very happy with how quickly they were developing this 10-year-old code base and like adding new features, modifying it, responding to business needs. But they slowed down, and the reason why they slowed down, they explained the reason for the decreasing quality of the test suite. They were looking for solutions. They found mutation testing, which worked very well for them. And this was 10,000 lines of a C++ code base. This was an unthinkable, 100,000 lines of a C++ code base. It was an unthinkable scale compared to things we typically, on average, deal with on a daily basis. And given that they were able to introduce something like this in a relatively rigid environment, I'm certain that we can introduce it in a Clojure world as well. If you'd like to try it, I encourage you. Line Mutate is a freshly pushed lining and plugin. You just type line, mutate, and if everything goes well, it will just print a nice Word diff of mutants, of survivors in your project, giving you hints where you might want to look into to improve the quality of your test suite. More information about the whole thing you will find under the main repository on GitHub. I encourage you to take a look. I encourage you to try it out and let me know if anything is unclear, if anything doesn't work for you. I would love to get your feedback. I would love to learn how I can make this thing work better in your setting. I hope that in this short presentation, I was able to encourage you to try mutation testing, that I was able to demonstrate that mutation testing is a viable method of evaluating quality of our test suite and increasing quality of our test suite by telling us exactly what things are missing, which cases aren't covered yet. There are problems. There are serious problems. Some of them are just, well, speed of mutation analysis, which leaves a bit to be desired. Some of them are more serious. For example, the problem of non-termination in certain cases. Tooling is there. It's all about trying it out. It's about filling in the missing gaps and connecting existing pieces together. I encourage you to give it a try. I would love to have your feedback. You've been a great audience. This is all I've got. Thank you all very much.
Any questions?
Yeah, thank you first for an amazing talk. And not only you found a actually quite obvious idea of mutation testing for a Clojure developer, quite obvious, but you like executed it in a very sophisticated way, finding the actual problems in real world. So to my question, I wonder if this would, mutation testing would not only show like discrepancies in the test coverage or test implementation, but also show you, like you showed with the missing function bodies giving valid results, that your implementation is maybe actually overcomplicated, like accidentally reducing your implementation to something more minimalistic while still being valid to the tests.
Something like shrinking from generative testing.
Like there's a code shrinking. Mutation testing is a way of kind of code shrinking. I think accidentally, but did you observe that? That would be interesting.
Very interesting. I haven't looked in this direction, but this is certainly an interesting path to explore. Thanks you for this comment.
Thank you.
It goes maybe in a similar direction. I wonder if you have any experience if this kind of testing generates different insights in comparison to classic test code coverage generation.
Not having a high test code coverage is surely a problem on its own. But having a high test code coverage is still not giving you enough information. Because all in all, a compiler has 100% code coverage, right? It's compiled all your code, but it doesn't mean anything. Similarly, your test suite could have executed all the code, but if assertions are missing, just execution gives you no information. And this is where mutation testing comes in, trying to actually break the code which you're executing and checking whether those assertions you should have will fire. So it gives you more information. It performs a more in-depth analysis compared to looking at line coverage. I hope this answers your question.
Which mutators do you deliver with your plugin, and how easy is it to write your own mutators?
I just have a handful of them. Those are mostly simple things which swap things like you saw and or. There are things which, for instance, remove arguments from your functions and other simple things. Writing new mutations is fairly straightforward. It's something which accepts a representation which I adopted from rewrite CLJ, that is a zipper over your code, and then you use this zipper data structure to return modified versions of the code. One more comment I'd like to add is, the point is, what I think is very important is that adding more mutants is as important as figuring out which mutants don't yield return on investment, which mutation operations are not yielding survivors in real-world projects. So something which I have in my mind is, in future, assemble a large code base of Clojure libraries at fixed versions, along with their source code, and then having it as a benchmark for every new mutation operator we want to introduce to the library. So that we can tell, okay, we introduced this new mutation operator. It's made the test suite that much longer, that much slower, and it gave us back that many mutants, that many survivors. Is it worth it? Is it worth to introduce this new complexity to the tool? It's also something which I would run on all the existing mutation operations I have inside of my own library.
Just as a point on top of that, maybe, is there a notion of types of either mutations or kind of classifications of code that's being mutated? Because certainly if you could know one or the other, then that would help with this fewer notion of what mutations are running.
I'm not sure I
okay,
understood.
So I guess there's two types, either the type of code that is under mutation tests or the types of mutations that are being applied. So I'm just wondering if there is categories of either the code or the mutations.
I haven't explored it, but I'll be happy to talk about it.
Please, yeah.
Yeah, sure.
Thank you.
Let's talk in the hallway track.
Any further questions? Well, thank you very much.
Thank you all.